Hello, and welcome to Circle Theorems 4. This one is on the Thales theorem. So, first topic 1, quick review. It's the review from my previous 3 videos. There are a few key circle theorems. The most basic one is that if we have 3 points on a circle like this, and we name them A, B, and C, angle ABC is equal to 1/2 of arc AC. Now we also expanded on this a bit in Circle Theorems 2, I believe. Or if we have a figure like this, ADBEC, then angle ABC is equal to 1/2 of arc AC minus 1/2 of arc DE. If B is inside the circle, like this, and this is B, this is A, E, D, and C, then ABC is equal to 1/2 of AC plus 1/2 of DE. Now, in Circle Theorems 3, we covered the cross ratio, which shows that if we have any 2 lines in a circle, I'm going to draw a line like that. Need 4 points in a circle, and we make lines from them. We'll angle them A, B, C, and D. Then we can prove that OA times OB, like length OA times length OB, is equal to length OC times length OD. And it's called the cross ratio. So now, our last bit of review, we also did this in Circle Theorems 3. If we have any 2 lines, this is Pascal's theorem, we have any 2 lines like this, I'm going to draw them not parallel so that makes more sense, and we put any 3 randomly spaced points on this line, so you could do something like that. And these are the primes in here. So we have A, B, and C, and then A, B, and C prime. If we draw lines between A, B prime, and C, A prime to B, A prime to C, and C prime to B, and C prime to A, what you'll find is that where these line segments cross, where AB and AB cross, which is right here, where BC and BC cross, and where AC and CA cross. And what you'll find is that all 3 points are collinear, which means that you can draw a line through all 3 of them. Straight line. Okay. Topic 2, we're going to be looking at the Thales theorem. So what I'm going to do is I'm going to draw a big circle. We have a circle, and I'm going to mark the center. Now, what this theorem states is that if O is the center, and this is if this line passes through the center, it's point B to point C. If line BC passes through the center, and there is a point up here at point A, and we draw lines like this, then this angle will be a right angle, always. Now, how can we prove that? Well, I'm going to draw a line between OA, like that. And let me mark these angles. This is angle 1, this is angle 2, this is angle 3, and this is angle 4. Now we know we're going to do somewhat informal proof here. Since we know that O is the center of the circle, OB, OA, and OC are all congruent, which means that angle 1 is equal to angle 2, and angle 3 equals angle 4. Now, the original way this was proved was that by showing that BAC was equal to 1/2 of BC, like this angle was equal to 1/2 of BC. Since BC was 180 degrees, it meant that BAC was 90. Simple as that, the same circle proof we've been using. But there's another way to prove it. Since, as I already said, that BOA and COA are isosceles, angle 1 is equal to angle 2, and angle 3 is equal to angle 4. And since ABC is a triangle, that means that angle 1 plus angle 2 plus angle 3 plus angle 4 is equal to 180. Now, because 1 is equal to 2 and 3 is equal to 4, we can say that angle 2 plus angle 2 plus angle 3 plus angle 3 is equal to 180. Group those up, so it's 2 times 2 plus angle 2 plus angle 3 equals 180. And then divide the 2, and that means that angle 2 plus angle 3 equals 180. Angle 2 plus angle 3 is angle BAC. So we know that angle BAC is equal to 90 degrees. Now, I want to do a quick application of this theorem before I move on to topic 4. Topic 3 is technically the whatever application. If we draw a circle, let me line up my paper. If we draw a circle like this, I'm gonna mark about where the center is so we can see how close we get on this. Now, I'm gonna use this box for this. You just need something that has a right angle to it. Now here's what we're gonna show. If we take this box and put it on the circle and mark like any point on the circle and put the corner of the right angle there, you see how it touches the other points of the circle. So it'll come over here and it'll come over here. If we mark where those points intersect the circle, we get something like this. See, look, if I put it back, you can't see the dot anymore. So now, if we take our ruler and we draw a line through the center, we know that the center to the circle must lie somewhere on this line. You see, I was a little off with the center placement and where the box is. You see, it would look like it would go through here, and this is a little sloped. So now what we can do, I'm just going to erase this. Now what we can do is, if we do it again from any other point on the circle, let's stay down here. I'll mark a point. It'll come up here, and it'll go over here. And if we draw a line between those 2 points, you see that our center of our circle is about right there. And if we take our circle thing back, now this is true, this has been proven to be true, but to see how close we really were, you can put our ruler right about there, draw a line across, and draw a line up. So the real center of the circle would be just above that. I think it's just because the point is pretty big, but we were still pretty accurate. Now, this will work every time because of the theorem, but in our case, we weren't precise enough. Plus, it's kind of hard to do. So now, for our last one, we're going to do an informal proof on proportional triangles, also using this theorem. So I'm going to draw a big circle again. My pencil. Draw a circle and mark about where the center is. Alright. We're going to draw a line across the circle. As long as this goes to the center, it doesn't matter which it is at this point. Mark point A up here and turn this into our triangle from our original application, our original theorem. Now, what this states, this is proportional triangles. Name this point B, this is point C, and this is point O. And then I'm going to draw a perpendicular line from point A along line BC to point D. I'm going to do this to show that it's perpendicular. Now, we can prove that all three of the triangles in this picture are similar. This right triangle, and this right triangle, which is kind of flipped upside down. Now here's how we would do this, and I'm just going to explain it because it's a lot to write. So, we know ABC is a right triangle, and we know triangle ADC is a right triangle. This is the small one. This is the big one to the small one. And both of the triangles share angle C, angle ACD. You see, this one has it as its top angle, the other one has it as its side angle. Both of them share this angle, which means that because they both have right angles and they both share the angle, they are similar by angle-angle similarity. Now, by the same reasoning, I'm going to do the big one and the medium one now. Both of them are right, both ABC and ABD, and they share angle ABC, this one over here, which proves that they are similar by, again, angle-angle similarity. Now, also, because both triangles ABD and ADC are similar to ABC, that implies that they're similar to each other, which means all three of the triangles in this image are similar. Bye, guys.